Okay, so our problem here is we have this series, this harmonic series, and we want to prove that it diverges. So this is a very useful result. In fact, the divergence of the harmonic series and the convergence of some p-series and some geometric series, these are kind of your home results when you're looking at convergence questions. These are the results that you return to again and again and again when you're doing comparisons and things like that. So we want to prove that this series diverges. So recall that the harmonic series is the series 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 and so on. Okay, so if we didn't know that it diverged, because I'm sure everyone watching this video knows that it diverged, or that it diverges. But if we didn't know that, how might we prove that? Well, we know that the geometric series, we know naively that the geometric series 1 plus a half plus a quarter plus an eighth plus a 16th, we know that that converges. And we can see that the harmonic series has extra terms, right? So instead of 1 plus a half plus a quarter plus an eighth, it has 1 plus a half, then plus a third plus a quarter, plus a fifth, a sixth, a seventh, and then an eighth. And so maybe one mode of attack is to compare it, not in the sense of a comparison test, but compare it informally to the geometric series. Okay, so what do I mean by that? Okay. If we write out this series, so let's write out a few terms here. The idea is that the geometric series just picks out, the geometric series with r equals 1/2 just picks out this term, this term, this term, this term, and it starts leaving out more and more terms. Now, merely to say that something is bigger than a series that converges is not, of course, enough to show that that series diverges. But maybe we can be a little bit more clever here, right? Because you can see that if I add in that extra term that the harmonic series has, that geometric series doesn't have, well, 1/3 plus a quarter is certainly greater than a half. Okay. And 1/5 plus 1/6 plus 1/7 plus 1/8, these are also greater than a half. Because what I'm doing here is I'm taking 4 terms, each of which is greater than or equal to 1/8. Let's say 1 of which is equal to 1/8, 3 of which are strictly bigger than 1/8. And so I have something that's strictly bigger than 1/8 plus 1/8 plus 1/8 plus 1/8. And I can do this ad infinitum. I can take the next 8 terms. That would bring me to 1/16. And I get 8 terms whose sum is bigger than 1/2. And then I take the next 16 terms. I get something that's bigger than 1/2, and on and on and on. And so what I get is I get a series that's bigger than 1 plus a half, plus a half, plus a half, and I keep on adding halves, right, by grouping these terms together in a clever way. And this, of course, very obviously diverges. So this is the proof. This is a proof that the harmonic series diverges. But because we have some board space left, maybe let's take a look at an alternate proof. Because if we, so one other way of looking at this is to sketch it, right? We can look at it on a graph, say. So here's an alternate take. Okay, so what I want to do is I want to add up the areas of these blocks. So that's the block of width 1 and height 1, then the block of width 1 and height 1/2, the block of width 1 and height 1/3, 1/4, and so on. So what we can do is we can use the fact that 1/x intersects the top left-hand corners of each of these. Now, if you were to do this as rigorously as you could, there'd be a little bit of work to show here. There'd be a little bit of work to show that this function is strictly decreasing, and so that these blocks are in fact, they have areas that are bigger than the area under the curve y equals 1/x from 1 to infinity. But maybe just looking at this very quickly, I hope you can see that the harmonic series, let me write it here. So the harmonic series 1 plus a half plus a third and so on this is bigger, strictly bigger, than the integral from 1 to infinity of 1 over x. And a little bit of work, so you take the antiderivative of that, you take the limit as one of the endpoints approaches infinity, and you can see that this thing blows up. Right? This thing goes to infinity. Very slowly, but it goes to infinity. And so this is kind of a second way, using integration, using the fundamental theorem of calculus, of seeing the fact that the harmonic series diverges. Two proofs, same result.